as I heat the fixed amount of gas in the flask, you can see that it increases its volume. And if I want to restore that hot gas to its original volume, then I have to increase the pressure by adding weight on top of the piston. Well, that's all very familiar stuff, and people have done a lot of work on the relationship between pressure, volume, and temperature for a gas. And if I were to do careful experiments along the lines of that simple demonstration, I'd find that volume is directly proportional to temperature, keeping the pressure constant, and also that pressure is directly proportional to temperature if I keep the volume constant. And as you know from the main text, it's possible to summarize these relationships in the ideal gas law. There it is. Now, N here, remember, is the number of moles of gas present. It's just a measure of the number of basic particles in the gas, and R is a constant. Well, this ideal gas law tells us very beautifully how P, V, and T are related for a gas, but it gives us no insight at all as to why gases should behave in this rather nice way. Well, there is a very simple model called the kinetic theory of gases that does give us a nice physical picture as to what's going on inside the gas. The idea is very simple. Think of a gas as being composed of lots of tiny molecules moving around at random. Then the pressure is due to these molecules, microscopic molecules, colliding against the wall. Well, that's a nice simple picture, but it's also rather abstract. And what we want to do in this program is to convince you and boost your confidence in the basic truth of that idea by showing you that it really works, even at a macroscopic level.
Well, this is our macroscopic model of the gas. We're using the pucks to represent the molecules, and they're all moving around at random, and we're keeping them jiggling with this frame, which simulates a constant temperature. But how does this model live up to all the assumptions of the kinetic theory? Well, I've already said that they're moving around at random, so that's okay, but they're also supposed not to interact with each other. Well, again, that should be okay. There's no reason why these pucks should attract or repel each other, except when they collide. Third assumption is that they should obey Newton's laws. Now, we've done that by using an air table, so the pucks are moving on cushions of air, and that reduces the friction, and so they do obey Newton's laws pretty well. But of course, the price we've paid is that we've had to go to a two-dimensional rather than a three-dimensional model. What else? Well, they are also supposed to, when they rebound with perfectly elastic collisions. And I think you can see that they're doing that pretty well. But of course, there are bound to be some losses, which is one of the reasons why we have to keep the frame jiggling, so that we exactly balance those losses. But of course, we'd be a lot happier about this whole system if we could get something even vaguely approximating the gas laws out of it. Well, let's see if I can. Suppose we think of this as being the cylinder. And suppose I treat this white board here as the piston of the cylinder. Now, I can apply some pressure to the piston with this string, which I can hook over the pulleys. And now we're applying a pressure via the string to the piston, which if I remove the support, will begin to move until it stops. And now you can see that what's happened is there's come a balance point where the little impacts of the pucks are just stopping the pressure of the piston, closing the volume completely. We have a fixed volume for a fixed pressure for a fixed temperature. Of course, if I increase the temperature, then the volume should also increase. And I can increase the temperature by increasing the jiggle speed. Let me do that. Well, I don't know whether you're absolutely convinced, but I think the volume has increased slightly. Perhaps not as much as we'd like, but then don't forget there's a problem here, because one of the other assumptions of the kinetic theory is that we should be using point molecules. Okay, so it does seem to be giving us at least something. Let's pursue this matter a bit further. Let me just put this back and anchor the whole thing again, because the beauty of this system is that we can now actually look into the system and see what individual molecules are doing. We can even follow one single molecule about, and that's even easier if I put in this blue-coloured one and then fade down the rest. You can see that sometimes it's moving very slowly, and then it suddenly speeds up after a collision, and then slowly, and then speeds up again. If you look at that one molecule for a long period of time, it has a whole range of speeds. Slow, fast, intermediate speeds. Now, of course, every time that molecule speeds up, there must be another molecule somewhere in the system which slows down if the whole system is in equilibrium. And from that, we would predict that if we looked at the whole ensemble of molecules, at any one instant of time, there should be a distribution of speeds. How can we test that?